Hello dear students, welcome to Pen and Paper Chemistry on YouTube. We are starting with D and F block elements. We shall be doing the general study and some specific compounds in this particular heading. For D and F block elements, now these are part of the periodic table. A rough plot of the periodic table is shown on the board. So we've got the S block elements. We've got the P block elements on the extreme right. The S block elements are group 1 and 2. The P block group 13 to 18. The D block elements are sandwiched in between the S and the P block elements, and that is why they are called transition elements. If you've got your fundamentals in place regarding the S and P block elements chemistry, you will realize that on the extreme left of the periodic table, we have highly electropositive elements, whereas on the extreme right of the periodic table, we have the highly electronegative elements barring the noble gases. Transition, change from S to P, from highly electropositive to highly electronegative, is what the D block is all about. Inner transition. When you study the transition elements, there comes a point where you have a set of 14 elements whose properties are entirely different from the elements existing in the transition elements. But as a whole, their properties are very much similar to each other. Secondly, this is a set of 14 elements. So if I fit them over here, my periodic table becomes very haphazard. And the whole purpose of organizing the elements, the 118 elements, in a systematic way so that their study becomes easy is completely lost. So what we've got here is a subsection of the transition elements of 14 elements is put at the bottom of the periodic table, and we name them as inner transition elements, as a subsection of the transition elements. There's another term given over here, the D block, the F block. What justifies their being called as the S block, P block, D block and F block is where the electrons are entering. So if I am talking about sodium atomic number 11, I have 1s2, 2s2, 2p6, 3s1. The last electron has entered into an S sublevel. The third energy level. So N is equals to 3, S is equals to 1, and this is the position being occupied by sodium in the periodic table. So hydrogen, lithium, sodium. Similarly, let's suppose I am talking about boron atomic number 5. So 1s2, 2s2, 2p1. Energy level 2, P1. So group number is 13. 10 plus 3 electrons in the valence shell gives me the group number. So boron, energy level 2, group number 13, and we have boron over here. Now this is just a touch base on the periodic table. This particular periodic table has been separately covered on the channel under a separate playlist of periodic table. If you are not very confident in this, I would request you to first understand the periodic table and then go ahead with it. Although it is a long video, I understand, but the entirety, it's the whole thing explained in that. Now let's go on to scandium. How do we write the electronic configuration of scandium? Those who are conversant with writing the electronic configuration in terms of the nearest inert gas, they can go ahead with that, right? So scandium atomic number is 21, nearest inert gas is argon atomic number 18, and then we have 4s2 and 3d1, right? Where did I get all this? This is actually based on the off-board table, which, as I said, is already covered on the channel under the heading of periodic table and atomic structure. So have a look at this off-board table, and if you are not sure about this, you can copy this. So this is the order in which the energy levels are filled up. If you feel that you are not able to understand D and F block elements, one of the reasons could be that you are not very confident about writing the electronic configurations. So please go ahead, learn this off-board table, the energy level diagram, which gives us the order in which the orbitals are filled up. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5s, 6d, 7p, 8s. I have done these in separate colors, so you advance from one color to the other, so it's easier to recall. Not easier to learn. Learning has to happen like that, but it's easier to recall when you relate it to a color. When I'm talking about scandium, so argon 18, we have 3p filled up. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? And then we go on to 3d1. Now the electrons have started entering into the D sublevel, 3d sublevel, right? So we will have the electronic configuration of the elements listed here. So if I write over here, scandium will be 3d1, right? The next element will be 3d2, third 3d3, next one, and don't forget the 4s2 with every. So 4s2, 3d2, 4s2, 3d3, 4s2, 3d4, right? Here the element I am talking about is chromium. Chromium, atomic number 24. Argon, 4s2, 3d4. Now comes the anomaly. Now comes the part which you have to remember. 4s2, 3d4. If instead of this 3d4 it was 3d5, then what would happen is this would be half filled, and half filled orbitals are extra stable. So how does it get 3d5? It goes to 4s and says, can I borrow one electron from you? So the catch is, the win-win situation is, you will also be half filled, I will also be half filled, and as an atom we will become very stable. So why should 4s not agree to it, right? It is making them stable as a family by helping out each other. So we write the configuration of chromium as 4s1, 3d5. So can you relate to why we are calling these elements as the D block elements, right? Go ahead, after this it will be 4s2, right? 3d5, because now naturally it has got the d5 configuration. 4s2, 3d6, 4s2, 3d7, 4s2, 3d8, 4s2, 3d9, that is my copper, atomic number 29. Again, see something over here. If in the case of copper, so what we've got over here is we've got copper, atomic number 29. Configuration 4s2, 3d9. Same situation as for chromium, right? So let's have the family sharing the burden so that it becomes a stable family. So copper atomic number 29 is 4s1 3d10. Fully filled extra stable, half filled extra stable. So copper we have, instead of 4s2 we will write it as 4s1 3d10. Correct? Go on to zinc atomic number 30, 4s2 3d10. Very extra stable because it has got fully filled s orbital and fully filled d orbital as well. Now if you notice in this transition series or in this series that we have written, the electronic configuration, the last electron is entering into the d orbital, right? So that d orbital or d sublevel is incomplete. Yes, here it is complete, but in its ionic form, it is incomplete, right? So if I am talking about Cu positive, of course it will lose the 4s1 electron. If I am talking about Cu positive, what will happen is, single positive, cuprous ion, it will lose electron from 4s, agreed. So 3d is complete. But what about Cu2 positive? It will have to lose one electron from the d or sublevel. With the result, the configuration will be 3d9. So that means it's an incomplete d sublevel. So we say the d block elements or the elements are in the d block are said to be so because either they have an incomplete d sublevel or d orbital in their elemental state, or any of their oxidized state, right? For example, in the case of Cu2 positive, it can be any of the oxidation states. They will have incomplete d orbital, right? That qualifies an element for entry into the d block. Now the objection is, talk about zinc. If I am talking about zinc, so let us see the configuration. Zinc, atomic number 30, configuration will be argon here and then 4s2, 3d10. Fully filled d orbital. Talk about Zn2 positive, it loses 4s electron, fully filled d orbital, right? Then what qualifies its position in the d block of the periodic table? Its properties, its behavior, its characteristics is what qualifies its presence in the d block. Always remember, periodic table is all about systemic organization of the elements known to us so that their study becomes easier. So what we've got is, just like there, the maximum capacity of the d sublevel is 10. So we will have 10 elements in this series. So here in this series, the electron is entering into the 3d sublevel. Hence, the first series starting from scandium to zinc is called as the 3d series. Go on to the next one, yttrium to cadmium. It will be called as the 4d series. Start from lanthanum to mercury. We will have the 5d series. Actinium to copernicium, we will have the 6d series, right? So you've got some points in place. Why are we calling them as the d block elements? How to write their electronic configuration? Because the same principle of half-filled and fully filled orbitals being extra stable applies to the elements further down the group. How do we number them? So I've got group number 1, group number 2. So we'll have group number 3, group number 4, 5, 6, 7, 8, 9, 10, 11, 12 and from 13 onwards, it is the P block of the periodic table. In the 3D series, how many elements do I have? Starting from 21 to 30, there are 10 elements. In the 4D series, I have elements from 39 to 48, again 10 elements. Come to the 5D series, we've got 57 to 80, right? So there is an extra set of 14 elements. This is what we were talking about. So let's understand this part as well. So I've come back to the energy level diagram once again. So we've got 1s, 2s, 2p. Okay, let me jump straight to 4d, 5p, 6s, and after 6s we should actually have the electron entering into 4f. But what we notice in the case of lanthanum, atomic number 57, is that the electron first enters into 5d. One electron goes into 5d, and then electrons start entering into 4f, right? So 4f maximum capacity is 14, right? And so we have a set of 14 elements down in the periodic table, starting from cerium to lutetium. Correct? You have to remember for lanthanum it is 5d1. So it's 6s2, 5d1. And then 4f1, 4f2, 4f3, 5, 6, 7, 8, 9, 10 till 14. And then we again come back to the transition element or the D block elements. Same way, the same anomaly is seen when you go a step down under the period number 7. So you have actinium, atomic number 89. So you will have 7s2, go on to 6d1, and then 5f, 1, 2, 3, 4. Starting from thorium to lawrencium. So you have 14 elements fitted down into the periodic table. According to the new recommendations of IUPAC, what they say is that we simply put 57 to 71 over here, and these are written as lanthanides, atomic number 57 to 71, and this part is written as actinides. I am talking about the latest ones, IUPAC recommendations 2018. So if in your books, if in your textbooks, it's slightly different where lanthanum is listed here and actinium is listed here and 14 elements are over here, it's okay. Please follow the system as advised by your curriculum. This I am only including just to apprise you of the latest developments. So according to the latest developments, lanthanum and actinium are a part of this F block, that is the inner transition elements, because their properties resemble the inner transition elements. Now, another thing to be observed over here. In the case of S and P block elements, the electron is entering into the valence shell. So, when I wrote the electronic configuration of sodium, check in your notes. You must be noting all this down. Are you noting this down? No? Oh, then how will you have something ready for reference later on? In your best interest, please make a note of whatever is being taught here so that you have your notes ready for reference when you are offline, right? So we wrote the electronic configuration of sodium 1s2, 2s2, 2p6, 3s1. Correct? Boron atomic number 5, we wrote 1s2, 2s2, 2p1. For scandium, we wrote argon 4s2, 3d1. Sodium boron, the last electron is entering into the valence shell. Scandium, the last electron is entering into the inner shell, which is also called as the penultimate shell. So we have this as the nucleus of the atom. These are the orbits. If my last electron is here, then an orbit inner to this, one step inner to this, is called as the penultimate. Two step inner to this, so this is called antepenultimate or inner penultimate. So when I write the electronic configuration of cerium, what will happen over here is cerium, the valence shell configuration will be, can you write it for me? Please go ahead, either in terms of the inert gas or in terms of the expanded notation. Although inert gas configuration is preferable, go ahead, pause the video, write the electronic configuration to get confident in this topic. Right? Does the electronic configuration match? You got it right? Very good. That brings a smile to your face. So cerium, in terms of the nearest inert gas, its atomic number is 58. So we'll have the nearest inert gas is xenon, atomic number 54, 55, 56, 57, 58. My valence shell is 6th one. Penultimate shell is the 5th one. The antepenultimate is the 4th one. So that is why they are called as the inner transition elements or the F block elements. So what will happen over here is the electron is entering into the F orbital of the inner penultimate shell. This brings us to something very, very interesting, and that is the shielding effect. Again, on shielding effect, there is a separate video on the playlist Atomic Structure. If you've not seen that, I would advise you to refer to that. I will explain a little bit, but the details are there on that video. What is shielding effect and what role does it play in the D and F block elements? Let's do that. Shield, protect, stop. That is the meaning of the word shield or screen. We know that in an atom, the nucleus has the protons in it. I'm not considering the neutrons because they are anyway neutral. The protons are positively charged, right? The electrons are present outside. I'm drawing a very simple circular structure so that it's easier to relate to, right? The electrons are present outside the nucleus. There is force of attraction between the protons and the electrons, right? That is what holds them in place. That accounts for the stability as well. The electrons which are in the inner shell, they are very possessive for the love of the protons. They say, everything should be ours. We don't want it to spread more and more. So, they prevent the force of attraction of this proton from reaching to the electron which is located further away from the nucleus. And that is all what is shielding or screening effect is about, right? The possessiveness of the inner electrons for the pull of the positively charged protons. What role does it play over here? More the electrons in the inner energy levels, more will be the shielding effect, right? When we are talking about the transition elements, just now we saw that the electrons Okay, in the S and the P block, the electrons are entering into the valence shell. In the D block, the electrons are entering into the inner valence shell. That means the penultimate shell. In the F block, the electrons are entering into the antepenultimate shell. With the result, the electrons in the inner shells is increasing. So what will happen? They will further reduce the attraction of the protons for the electrons. Right? But what we have to remember over here is the shielding effect of the S electrons is more than that of P, is greater than that of D, and the weakest is for F, because S electrons are very much focused. We are spherical, that's it. We are not moving here and there. P, they are spreading out now, right? They have a dumbbell shape. So with the result, they are spreading out and their concentration is becoming less. If you recall the shape of D, they are spreading out, they are diffusing out even more. So their focus, so they are not concentrating on the war that is going on. Their focus is here, there, everywhere, right? F is even more complex. So although by virtue of their position in the inner orbitals, they should be preventing the attraction between the proton and the electron, the valence electron, they are not able to do so as effectively as the electrons in the S and SP or D sublevels. What consequences does this have in our study of D and F block elements? Let's see that in video number 2. Stay tuned as I load the next video. But I feel that once these basics are in place, you should be able to connect to this particular topic. Also, if you can, before the next lesson, please make a periodic table like this. Just take an old chart paper. If you can, make the periodic table displaying all the groups, the periods, the elements, and have it ready. It's not necessary that you need to have this big a chart paper. You can do it on an A4 size sheet as well. Just keep it handy so that whenever I refer to an element, you are able to quickly see it, because I will not be able to put this on the board while I am teaching. I need this help from you. Please write the elements with their electronic configuration and keep your periodic table handy. By the way, it will come in useful when you are doing the P block elements as well. So why not just do it? See you in the next video. Stay subscribed, stay tuned, and share the joy of learning.